So now let us start the last part of two element array, equal amplitude and opposite phase. Total field we have already seen, ET is equal to 2j E0 sin psi by 2. So from where we get this? 2j E0 sin psi by 2. How do you get this? The question is this. The answer is very simple. Now psi is equal to, as we have seen already, psi is equal to k delta cos theta by 2 plus alpha. Now alpha, in the previous case alpha was 0. In this case alpha is equal to 180 degree. So if you put alpha is equal to 180 degree, then the total field, total far field ET is equal to 2 E0 cos psi by 2. There we are adding plus 180 degree. Since you add 180 degree cos theta plus 180 degree, that gives you sin theta. So from that we get this 2j E0 sin psi by 2. Then since we get 2j E0 sin psi by 2, for psi we write k delta cos theta by 2, that we write. So that way we will get E max sin k delta cos theta by 2. Okay. So ET is equal to E max, when ET will be E max, when sin k delta cos theta by 2 is equal to plus minus 1. Sin k delta cos theta by 2 will be plus minus 1, under which condition we will consider the difference between the two sources, or the separation between the two sources, to be lambda by 2, or half wavelength separation. Then for delta, if we put lambda by 2, k delta is equal to 2 pi by lambda into lambda by 2, that is pi. So pi cos theta by 2, and that should be equal to pi by 2. So if you do that, then pi by 2 cos theta max is equal to plus minus 2n plus 1 by 2 into pi. So 1 by 2 pi that cancel out. Cos theta max is equal to plus minus 2n plus 1. So that will give us, for n is equal to 0, cos theta max is equal to 1. Cos theta max will be 1 when theta max is equal to 0 degree or 180 degree. Similarly, ET is equal to E mean if sin k delta cos theta by 2 is equal to 0. If that is equal to 0, then we can, as in the previous case, we will get for delta is equal to lambda by 2, or half wavelength separation, we will get pi by 2 cos theta mean is equal to plus minus n pi. This is just opposite of the previous case. In the previous case, we were getting theta max, for cos theta max it was n pi. Now for cos theta max it is 2n plus 1 pi by 2. In the previous case, for cos theta mean it was 2n plus 1 pi by 2, here it is n pi by 2. So for n is equal to 0, again theta mean is equal to 90 degree or 270 degree. Okay. Now for half power, again when power is half, voltage or current is 1 by root 2. So to get that, for half power point, sin k delta cos theta by 2 is equal to plus minus 1 by root 2. So now solve that. For delta is equal to lambda by 2, or separation of lambda by 2, then we will get pi cos theta by 2 is equal to plus minus 2n plus 1 pi by 4. So for n is equal to 0, we will get HPBW, half power points, there they will be 60 degree or 120 degree. 60 degree and 120 degree. So if we plot the polar plot for the array factor, now the maxima will be along 0 degree or 100 and 180 degree. Minima will be along 90 degree and 270 degree. You can see that we have two sources along the z axis. Z axis is theta is equal to 0, theta is equal to 180 degree. So that is the z axis. The two sources are there. Maxima are along the z axis and minima are perpendicular to the z axis. So since the minima is perpendicular to the z axis, or null is perpendicular to the z axis, maxima is along the z axis or the array axis, This is an end fire array. So equal amplitude and opposite phase gives us end fire array. Half power beam width will be between 120 to 240. So 240 minus 120, that will give us 120 degree. So beam width is, half power beam width is 120 degree. Okay. So now let us see the next part is the Cartesian plot and the polar plot. So you can see the Cartesian plot and the polar plot for the array factor and the normalized array factor. I am not going to discuss it anymore because we have already discussed it for the equal amplitude and equal phase. Now let us come to non-isotropic sources. Isotropic sources we have considered, two isotropic sources. Now suppose we have two non-isotropic sources. They are of equal amplitude, but sources are not isotropic. Since sources are not isotropic, each source will have its own radiation pattern. Only condition here is the radiation pattern of each source is same. So here let us say we are taking two short dipoles. One dipole is at 0.1, other dipole is at 0.2. Difference between them or separation between them is lambda by 2, and they are from angle Z to Y is this angle is theta. So everything remains same except instead of point source we have short dipoles. Now in this case what will happen? If the sources are not in phase, both the sources are not in phase, then psi is equal to k delta cos theta plus alpha. This we know. Now let E0 is equal to Es sin theta. So they are not isotropic, therefore Es sin theta. Otherwise E0 will be a constant. If they are isotropic, they will be constant. Here in this case we are considering it to be Es sin theta. Es is the amplitude of the source, sin theta is the pattern, or Es cos theta. So any of these two. Then Et will be 2E0 cos psi by 2. So for that we will write 2E0. For E0 we will write Es sin theta or Es cos theta. Let us write Es sin theta. So it is 2Es sin theta into cos psi by 2. Or you can say 2Es cos theta into cos psi by 2. Now look at this. The array factor portion is now no more cos psi by 2, it is sin theta into cos psi by 2. Cos psi by 2 is the array factor. The other part is the pattern of the source. Source pattern is sin theta, it can be hemisphere, it can be cos theta, anything. So Et is equal to pattern of the source, which is Es sin theta, 2Es sin theta or 2Es cos theta. That is the pattern of the source into the array factor. Right? This gives us, so you can see pattern of the source into array factor. Array factor remains as it is, cos psi by 2. Only thing is we have multiplied that with the pattern of the source. This gives us to a very important concept in array theory, which is called the pattern multiplication. Pattern multiplication. Now look at this figure. This is one pattern. This is pattern of one antenna. Okay. That we are multiplying with the array factor. This is the array factor. End fire direction is the array factor is in the end fire direction. Pattern of the antenna is the donut shape. That is going to give us the resultant pattern. So resultant pattern will be how? How you will get the resultant pattern? Wherever there is 0 or null in either of the patterns, there you will get a null. When there is no null, then you will get the multiplied value of the first pattern into the non-zero value of the second pattern. That will give you the value. So this is what is pattern multiplication. The principle is stated in this form. The field pattern of an array of non-isotropic but similar sources is the product of the individual source pattern with the array factor of the isotropic point source of this same at the same location, relative amplitudes and phases as the non-isotropic point sources. This is called the principle of pattern multiplication. Okay, this is another example. You are getting a fan beam here. Then there will be another example. You can see those were the 3D examples. These are the 2D example. A is sine theta, B is cos psi by 2. Multiply them, they are giving you E sine theta cos pi by 2 into cos theta. This is 2D example. Another example is this, of course, sine theta, cos theta. Second one is cos theta. If I take cos theta into cos psi by 2, that is going to give us the other part, the flower-like shape. Okay. So with this, we come to the end of two-element array. So that concludes the two-element array. Now we will come to n-element linear uniform array of point sources. We will consider point sources, then we will go to pattern multiplication. So what we have here is n isotropic point sources. N isotropic sources, their location is linear, so they are on a straight line. Equispaced between any two consecutive source, the separation is delta. So equispaced. Phase shift is progressive alpha. So first one phase is 0, second phase is alpha, third phase is 2 alpha, fourth element phase is 3 alpha. This way the phase progresses. So we have got progressive phase shift. Then psi is equal to k delta cos theta as in the previous case. And the psi does not change, psi remains same. You can see the figure here. So it is along the z-axis. The points are along the z-axis, separated by an amount of delta from each other. They are pointed towards the observation point P, and you can find out the path difference between any two consecutive points is delta cos theta. So depending on that, psi is equal to k delta cos theta. Then plus alpha is the phase due to the each source. So progressive phase. So that gives us psi is equal to k delta cos theta plus alpha. Now let us find out what will be the array factor. First thing is, let us find out what will be the array factor. So array factor will be Et is equal to E0 plus E0 exponential j psi plus E0 exponential 2 j psi plus that way up to, if there are n number of elements, then the final will be E0 exponential j n minus 1 psi if there are n elements. Take E0 common, then within bracket we can write 1 plus e to the power j psi plus e to the power 2 j psi up to exponential j n minus 1 psi. So from that you can say what is the array factor, Et by E0. Et by E0 is equal to the array factor. Array factor is equal to 1 plus e to the power j psi plus e to the power 2 j psi up to e to the power j n minus 1 psi. Now if you look at the terms within the bracket, they are like 1 plus r square up to r to the power n minus 1, which is a geometric progression where r is equal to e to the power j psi. If I write r is equal to e to the power j psi, then it is of the form 1 plus r square up to the term r to the power n minus 1. Okay, so it is a geometric progression. As you know, if it is a GP, the summation of GP is equal to 1 minus r to the power n divided 1 minus r. So array factor will be equal to 1 minus exponential j n psi by 1 minus exponential j psi. In the numerator take exponential j n psi by 2 common. In the denominator take exponential j psi by 2 common. So that gives you exponential n by 2 psi, exponential j n by 2 psi divided by exponential j psi by 2 as the term 1. The second term has a numerator and denominator. Numerator is exponential j n psi by 2 minus exponential j n psi by 2. So of course, sorry, the first term is exponential minus j n psi by 2. Second term is minus exponential j n psi by 2 divided by denominator is exponential minus j psi by 2 minus exponential j psi by 2. In the numerator and denominator you can multiply minus 1. So from that you will get the first term will exponential j n by 2 psi divided by exponential j psi by 2. That gives us the exponential j n minus 1 by 2 psi. So that term is there. Then the numerator part is sin n by 2 psi. Denominator is sin psi by 2. Okay, so array factor amplitude, if I take the amplitude then the exponential part will be 1. So array factor amplitude is equal to sin n by 2 psi divided by sin psi by 2. That is the amplitude of the array factor. That and the angle of the array factor, angle means phase, that is equal to n minus 1 by 2 psi because we have exponential j n minus 1 by 2 psi. So that gives us the angle. The phase factor is exponential j n minus 1 psi by 2 in this array factor. This phase factor is this. This is not important in terms of finding the amplitude. If the array output signal is not combined with the output signal of another antenna, this phase factor is not important. And this represents the phase shift of the array's phase center relative to the origin. That is its importance, physical significance. And this will be 1 if the origin coincides with the array center. In that case, the phase factor will be 1. So that will be automatically eliminated. Now we have found out the expression for array factor. Let us normalize that. So we'll do that. Okay, just. So up to now we have found out what is the array factor if we have n number of isotropic sources and they are linearly placed along an axis, and they are not only linearly placed, they are equispaced from each other and the phase difference is same, progressive phase difference. Now for normalization we neglect the phase factor PF, which is exponential j n minus 1 by 2 psi. So neglect that. Then array factor is equal to sin n psi by 2 by sin psi by 2. That we can approximate as sin n psi by 2 by psi by 2, for small psi or for large n. If you have large number of elements, or if psi is small, then as you know, as theta goes to 0, sin theta by theta approaches 1. So sin theta by theta is approximately equal to 1. When theta goes to 0, or sin theta is approximately equal to theta for small theta values. So using that concept, we can say Array factor is equal to sin n psi by 2 by sin psi by 2, that is approximately equal to sin n by 2 psi divided by psi by 2. This is in most practical cases you will get a small psi or you will get large number of n. Therefore, there is no problem in making this approximation. Then also we can say that array factor is equal to multiply n in the numerator and denominator. So array factor will be n sin n psi by 2 divided by n sin psi by 2. If we plot this value, fx is equal to sin n theta by n sin theta, this is n psi by 2. So psi by 2, let us take that as theta. So if we plot that value, sin n psi n theta by sin theta, or sin n alpha by sin alpha, n sin alpha, the plot will be like this. The plot that you see on the right hand side, that will be the nature of the plot. Now what we have done here is we have drawn the plot for different n. N is equal to 3 is the red, n is equal to 5 is the green, n is equal to 10 is the blue. So as you can see, as we keep on increasing n, the beam width or the maxima, that you can see that becomes narrower. As you decrease, it becomes wider. Similarly, as you increase the n, then the first null comes closer to 0. As you decrease, it goes away from 0. These are the two observations that you make. So what we have done is fx is equal to sin nx by n sin x. We have plotted this. This as maxima when fx or f is maximum. When will be f maximum? This will be maximum at x is equal to 0, x is equal to pi, x is equal to 2 pi. Those are the points where it will be maximum. So maxima points are found out in that manner. Now array factor, normalized array factor is equal to sin n psi by 2 divided by n sin psi by 2, that is approximately equal to sin n psi by 2 divided by n psi by 2 for small psi or large n. This is what is the normalized array factor. This neglects the phase factor. Now let us find out what are the nulls of this array factor. For null, array factor must vanish. So array factor normalized is equal to 0 for nulls. Now array factor normalized is sin n psi by 2 divided by n sin psi by 2. So that will be equal to 0. If that is equal to 0, then and n is not equal to 0, definitely n will not be equal to 0, because when n is equal to 0, then there are no elements. There is no point in considering this. So when n is not equal to 0, and n psi by 2 will become plus minus small n pi. And that will make AFN is equal to 0. So that gives us n by 2 psi is k delta cos theta m plus alpha. Small m indicates minima. So k delta cos theta m plus alpha is equal to plus minus n psi, and that gives you the null, or theta m now becomes cos inverse of 1 by k delta into minus alpha plus minus 2n pi by capital N. Now this value, this 1 by k delta, limit on that is 1 by k delta minus alpha plus minus 2n pi by capital N. That should be between minus 1 and plus 1. So that is the limit on that. Now let us take n is equal to 1, 2, 3, etc. If we take n is equal to 1, 2, 3, etc., but you cannot have n is equal to 0, or capital N or 2n or 3n. Those are the values which are excluded. That you can see from the expression also. If n is equal to 0, then theta m is equal to cos inverse 1 by k delta minus alpha. When alpha is equal to 0, that will be 1 by k delta. That cannot be found out. So n is equal to 0, capital N, 2n, 3n. In those points, cos inverse cannot be obtained. You cannot obtain cos inverse value. Therefore, those are excluded value. N is equal to 1, 2, 3, 4, etc. accepted value except these values. So these are the, at these points, 0, n, 2n, 3n, there you will get the maxima. Minima is n is equal to 1, 2, 3, 4. They give you the minima. These are giving you the maxima point. Now, since we know what these are the maxima point, let us find out what is the major maxima of the array factor, which corresponds to the principal lobe. This will determine the major maxima of the array factor of the principal lobe. That actually determines the direction of maximum radiation. The other maximas are the side lobes. They correspond to side lobe. So this gives us the our direction of maximum radiation, therefore maximum directivity. Therefore, we find out from this the half power beamwidth. Where they will occur? They will occur when psi by 2 is equal to 1 by 2 k delta cos theta capital M plus alpha. This will be equal to plus minus m pi. So from this you will get theta m is equal to cos inverse 1 by k delta into minus alpha plus minus 2m pi. Now m is equal to the order of maxima. M is equal to order of maxima, that will be 0, 1, 2, 3, 4, etc. provided AF is equal to 1. So they are not maxima of the minor lobes. Remember this. These are the order of maxima, but they are not the maxima of the minor lobes. Now we'll come to the secondary maxima, or the side lobes. Maximum of array factor normalized. When array factor normalized is less than 1. When it is equal to 1, you get the maxima, principal lobe. When it is less than 1, then we get the side lobe. Array factor beyond the first lobe, first null. These are the array factors which are beyond the first null. Then the numerator of array factor is a maximum. This is also called the minor lobe or the side lobe. When it will occur, the occurrence will be sin n psi by 2 psi is equal to plus minus 1. So that you can see f psi is equal to sin n psi by 2 by n sin psi by 2. Psi is equal to kt cos theta plus beta or alpha. So that plot again we have plotted here. So that will give us n by 2 k delta cos theta s plus alpha is equal to plus minus 2s plus 1 pi by 2. S is an integer. So from that you can get theta s. S gives you 1, 2, 3, 4, etc. 0, 1, 2, 3, 4. So those are the first minima, second minima, or first side lobe, second side lobe, third side lobe, etc. So cos theta s is equal to cos inverse 1 by k delta of minus alpha plus minus 2s plus 1 by n pi. So that you can rewrite in this manner. Grating lobes, theta s is equal to also. So from this you can say theta s is equal to pi by 2 minus cos inverse 1 by k delta into minus alpha plus minus 2s plus 1 by n into pi. Then comes the grating lobe. Grating lobe, actually you don't require the grating lobe, just for the concept, remember that any pattern that we design an array for, that pattern should preferably have a single major lobe or single principal lobe. If there are more than one principal lobe, then those lobes are called grating lobes. That is not a desired thing. Just remember that. Otherwise, grating lobes will be coming in your third semester when you will consider complete antenna part there we will consider about and grating lobes. So we will leave this part. Next, 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 next. Then half power beam width of the major lobe or the principal lobe. The half power beam width or the HPBW for the major lobe, that gives the difference between the points on the main lobe where the power is half of the maximum. That is half power beam width. So AFN is equal to 1 by 2 to the power half or 1 by root 2. For approximation, if we approximate AFN, then we will get n by 2 psi is equal to n by 2 into k delta cos theta h. Theta h is for half power beam. So cos theta h plus alpha, that is approximately equal to 1.392. That is the point where it will be half power beam width. So from this you can find out what is theta h. Theta h is equal to cos inverse 1 by k delta into minus alpha plus minus 2.782 by n into pi. That gives us the half power beam width. For symmetrical pattern around the theta m half power beam width, we will get half power beam width is equal to 2 theta m minus theta h. Theta m is the maxima angle and theta h is the half power point. So their difference into 2 gives us the half power beam width. And then we will come to broadside array. Broadside array, as I told you already, maximum direction is normal to the array axis. So element and array factor maxima for theta is equal to 90 degree. If it is broadside, then theta has to be 90 degree because maximum direction will be normal to the array axis. For array maxima, psi is equal to k delta cos theta m plus beta, that is equal to 0. Psi has to be equal to 0. If psi is equal to 0, then we will get the maxima. This is valid for the 0th order maxima or the principal maxima. Small m is equal to 0. So if theta m is equal to pi by 2, then cos theta m is equal to 0 and alpha is equal to 0. Alpha is equal to 0 means they have to be in phase. And there is no phase difference, they have to be in phase. So all elements have their excitation with same phase. So there is no progressive phase difference, phase is same. The uniform linear array has its maxima radiation at 90 degree when alpha is equal to 0 and cos theta m is equal to 0. For no grating lobe, forget this, delta has to be less than lambda. That is why we took lambda by 2. The separation between 2 point sources that we consider lambda by 2 is to suppress the grating lobe. Delta has to be less than lambda. Next. These are for grating lobe, so leave this out. This shows you the numerator, that is sin n psi by 2. The red part on the left hand side is the sin n psi by 2. Below is the denominator, which is sin psi by 2. So numerator and denominator, their plots are shown here. Then numerator by denominator gives you the array factor. So array factor and normalized array factor both are shown here for the broadside array. Next. So array factor for different number of elements are shown here. N is equal to 1, 2, 5, 10, 15. So you can see as you keep on increasing the number of elements, the beam width becomes gradually narrow, and the higher the number of elements, the narrower is the beam. So it will be, if you want a pencil beam or if you want a very narrow beam, then you should have very large number of elements. So it will be very narrow and it will go to a very large distance. Then we will come to the end fire array. End fire array is maximum direction is along the array axis, that is the main point. Element and array factors maxima for theta is equal to 0 or theta is equal to 180 degree, because that is where the array axis lies. Z is Z, array axis is Z axis, For Z axis, theta is equal to 0 or 180 degree. For array factor maxima, theta has to be 0. So since theta is equal to 0, psi is equal to k delta cos theta m plus alpha, or theta is equal to 0. That gives us k delta cos theta is equal to 0, cos 0 is equal to 1. So that is k delta plus alpha is equal to 0, or k delta is equal to minus alpha for theta m is equal to 0. Theta m has to be 0 for the end fire array. For array factor maxima, theta is equal to 180 degree, then we will get k delta cos theta m plus alpha, or theta is equal to 180 degree. If you put theta is equal to 180 degree, cos theta m is equal to minus 1, therefore minus k delta plus alpha is equal to 0. This is not beta, this is actually alpha. So plus alpha is equal to 0, or k delta is equal to alpha for theta m to be 180 degree. So both the conditions for end fire array we have got here. Now let delta is equal to n lambda, n is greater than equal to 1, 2, etc. If delta is that, then we will get additional main lobes or the grating lobes in the broadside direction. For no grating lobes, delta should be less than lambda, that we have discussed. Then this shows you the numerator and the denominator patterns, then the array factors, and this shows you the array factor. Then directive and fire array, this is not in your course, so leave it out. Directive and fire array, let us leave it out. So with this, we come to the end of array theory, antenna array theory. We come to the end of antenna array theory. Next time, we will discuss about the dipole antenna design using HFSS. That we will discuss. So we will see practical dipole antenna design using HFSS, that I will show you.